Invariance property is a useful and nice property of an estimator which can make the estimation of different parametric function easier. Fortunately, MLE has this property. In this module, we will discuss how it is possible along with some applications of this property for MLE. We will also formally introduce the likelihood equation and some interesting properties related to it. In this module, we begin with another important and useful property of maximum likelihood estimator, and that is called the invariance property. Let us begin with the statement of invariance property. Let theta hat be the maximum likelihood estimator of theta and omega be the corresponding parameter space. Then, for the parametric function g theta, which is a mapping from the set omega to capital gamma, the MLE of g theta is g of theta hat. As a proof, let us define another set omega gamma, which is equal to the collection of those theta for which g theta is equal to gamma. Then naturally, the whole parameter space omega is equal to the union of all omega gamma, gamma belonging to the set capital gamma. Again, let us define capital M of gamma is equal to supremum of Lx theta, theta belongs to the parameter space omega gamma. Naturally, mx gamma is the likelihood function induced by the function g. Now, our objective is to find the estimate of gamma, say gamma hat, at which the function mx gamma is maximized. Now, mx at the point gamma naught hat is equal to supremum of Lx theta, theta belonging to omega gamma naught hat, where omega gamma naught hat is the collection of those theta for which g theta equal to gamma naught hat. Naturally, supremum of Lx theta is greater than equal to Lx theta for all theta belonging to the set omega at gamma naught hat, and that is nothing but our likelihood function Lx at theta hat. Let us denote this inequality by say star. As g of theta hat equal to gamma naught hat, so theta hat also belongs to the set omega at the point gamma naught hat. Again, we consider another inequality. Here, we can also say that the function mx at the point gamma naught hat is less than equal to supremum of Lx gamma hat for all gamma hat belonging to the set capital gamma. Now, using the formal definition of mx gamma hat, this equal to supremum of gamma hat belonging to omega, again supremum of theta belonging to the set omega at the point gamma naught hat of the function Lx theta. Now, combining these two supremum, we can say this equal to supremum of all theta belonging to the parameter space omega of the likelihood function Lx theta, and obviously that is nothing but the likelihood function at the point theta hat. This inequality is denoted by say double star. Therefore, combining star and double star, we can say that the function mx at the point gamma naught hat is nothing but the likelihood function Lx at theta hat, and that is equal to supremum of the function mx gamma over all gamma belonging to the set capital gamma. This implies gamma naught hat in true sense of term maximizes the function capital mx gamma. So this implies gamma naught hat is the maximum likelihood estimator of gamma. but gamma naught hat is nothing but the function g at theta hat, and gamma is the function g theta itself. So finally we can say that g of theta hat is the maximum likelihood estimator of the parametric function g theta. Now, as an implication of this property, we can say that invariance property is widely used in maximum likelihood estimation. Using this property, we can get easily the maximum likelihood estimators of any parametric function, no matter how simple or complicated it is. Now we will consider some nice applications of invariance property in our theory. Let x1, x2, xn be IID binomial 1p variables, that is the Bernoulli p variables, where 0 less than equal to p less than equal to 1. Now, from the property of binomial distribution, we know variance of any random variable x is equal to p into 1 minus p, where x follows binomial 1p. Now this p into 1 minus p can be considered as a parametric function gp of p. Obviously, here p is the only parameter in the distribution. Also, we have studied that under Bernoulli sample observation, the maximum likelihood estimator of p is nothing but the sample mean x bar. Now, using invariance property, we can say that the maximum likelihood estimator of variance of x equal to the maximum likelihood estimator of p into 1 minus the maximum likelihood estimator of p, that is equal to x bar into 1 minus x bar. Next, consider a random sample of size n from an exponential distribution whose mean is beta. It is given, suppose that only k of these n observations are less than equal to capital M, where k is a positive integer strictly less than n and capital M is a known positive number. Suppose we want to find the maximum likelihood estimator of the unknown exponential mean beta based on these sample observations. Then, how to get this maximum likelihood estimator of beta? Let x1, x2, xn are those random sample observations which follow exponential distribution with mean beta. Then, corresponding to this x1, x2, xn, let us define a set of indicator variables y1, y2, yn defined as yi equal to 1 if xi less than equal to capital M and equal to 0 if xi greater than capital M. Then, naturally, y1, y2, yn will follow independently and identically Bernoulli theta distribution, where 0 less than theta less than 1. Now, theta will be here probability that any random sample observation xi less than equal to capital M, and that is equal to 1 minus e to the power minus m by beta under exponential probability model. As theta equal to 1 minus e to the power minus m by beta, then we can easily get that beta equal to minus m divided by log of 1 minus theta, which is nothing but a continuous function of theta. Also, we know from Bernoulli sample observations, the maximum likelihood estimator of Bernoulli probability of success theta is the sample mean y bar, which is equal to summation yi by n, and here summation yi is equal to the number of cases where an xi is less than equal to m. Hence, as a result, y bar is equal to number of xi less than equal to m divided by n. Now, from given data, we know that the number of sample observations xi's which are less than equal to m is k, and that is why the sample mean y bar equal to k by n. So, automatically, the maximum likelihood estimator of theta equal to k by n. Hence, by invariance property, the maximum likelihood estimator of beta will be minus m divided by log of 1 minus k by n. Now we go to the formal definition of what is called likelihood equation. Let Lx theta be the likelihood function of theta for fixed data x. Then small lx theta, which is equal to log of capital Lx theta, is called the log likelihood function of theta. Suppose the first order derivative of capital L theta or small l theta exists. Then the equation del theta of Lx theta equal to 0 is called the likelihood equation. Any maximum likelihood estimator of theta is a root of the likelihood equation, because by maxima minima principle, any maximum likelihood estimate should primarily be a stationary point, because it is maximum likelihood estimator which maximizes the likelihood function, and by maxima minima principle, to maximize the likelihood function, the first order derivative of the likelihood or log likelihood function should necessarily be 0. Any root of the likelihood equation may be local minima or local maxima. As a possible verification for the root theta hat to be an MLE is nothing but the second order derivative of capital Lx theta or small lx theta with respect to theta at the point theta equal to theta hat should necessarily be negative. Next we go to the likelihood equation for vector valued theta. Let theta equal to theta 1 up to theta s, which is a vector valued parameter. Then the likelihood equations will be the first order derivative of capital Lx theta or small lx theta with respect to theta I equal to 0 for all I from 1 to s. So that means here we will have s likelihood equations. As a possible verification for the root theta curl hat to be a maximum likelihood estimator of theta, we can define the Hessian matrix, which is nothing but the second order derivative of the likelihood or the log likelihood function with respect to theta I theta j at the point theta I equal to theta I hat and theta j equal to theta j hat for all I from 1 to s for all j from 1 to s. Then theta hat will be the maximum likelihood estimator of theta provided the Hessian matrix is a negative definite matrix. Next we go to an important result related to likelihood equation. Let capital T be a sufficient statistic for the family of distributions small f theta, theta belongs to the parameter space omega. If a unique maximum likelihood estimator of theta exists, it is a non-constant function of capital T. On the other hand, if a maximum likelihood estimator of theta exists but is not unique, one can find a maximum likelihood estimator that is a function of T. As an outline of proof, we can say, since T is sufficient, using Niemann-Fisher factorizability criteria, we can say the likelihood function L theta, which is by functional form nothing but the joint PDF or PMF f theta x curl is equal to g theta at t of x curl into the function hx curl for all x curl, for all theta, and for some h and some function g theta, where L theta is the likelihood function of theta and f theta x is the joint PMF or PDF of the sample observations x curl equal to x1, x2, xn. If L theta is maximized by a unique maximum likelihood estimator theta hat, then naturally it will also maximize the function g theta of tx, because only g theta of tx involves theta and hx is independent of theta. This implies naturally theta hat should depend on the sufficient statistic t, that is, it should be a function of the sufficient statistic t. Similarly, if maximum likelihood estimator of theta exists but is not unique, then there exists some maximum likelihood estimator theta that can be expressed as a function of t. Next we go to another important result. Under regular estimation case, if an estimator theta hat of theta attains the Cramer-Rao lower bound for the variance, the likelihood equation has a unique solution theta hat that maximizes the likelihood function. That means theta hat is the unique maximum likelihood estimator of theta. This result can be considered as the criteria of uniqueness of the maximum likelihood estimator. As a proof, let L theta denote the likelihood function of real valued parameter theta given the sample observations x curl equal to x1, x2, xn. Now, if f theta x curl denote the joint PMF or PDF of the sample observation vectors x curl, from the equality condition in Cramer-Rao inequality, we can get that the partial first order derivative of log of f theta x curl with respect to theta is equal to some function k theta into the estimator theta hat minus theta. Now this expression says that theta hat is the minimum variance bound estimator of theta, and as it exists according to the result, so it is also the minimum variance unbiased estimator of theta. Since by functional form, the joint PDF or PMF f theta x curl and the likelihood function L theta is same, so the previous equality relation can alternatively be written as del del theta of log of the likelihood function L theta equal to k theta into theta hat minus theta. For the sake of our ease, we can denote this expression as, say, star. Now, this expression, that is star, holds with probability 1. This implies the likelihood equation del del theta of log of the likelihood function L theta equal to 0 has the unique solution theta equal to theta hat. Differentiating both sides of star again with respect to theta, we get del squared del theta square of log of L theta equal to k dash theta into theta hat minus theta minus k theta. Hence, at the point theta equal to theta hat, naturally this second order derivative will become simply minus k at the point theta hat. Let us denote this expression by double star. Now, if t is an unbiased estimator of a real valued estimable parametric function g theta, then we can say that integration of tx into PDF fx dx equal to g theta. If the parametric function g theta is differentiable at least once, then from Cramer-Rao regularity conditions, we directly get by differentiating both sides of the above expression with respect to theta that integration of tx into del del theta log of fx dx equal to g dash theta. Now, in particular, choosing g theta equal to theta and noting that expectation of del del theta of log of the likelihood function L theta equal to 0 under the regularity condition, we get expectation of tx minus theta into del del theta of log of capital L theta is equal to g dash theta, which is equal to 1 with the choice g theta equal to theta. Let us denote this expression by triple star. Finally, we can substitute Tx minus theta as k theta inverse into del del theta log of L theta. Now we can think that how this substitution is possible. It is easy to observe. If we look at the expression star, then Tx behaves like theta hat x by its definition, and substituting Tx minus theta equal to k theta inverse into del del theta log of L theta x, we get from triple star that k theta inverse into expectation of del del theta log of L theta whole square equal to 1. That is, k theta equal to expectation of del del theta log of L theta x whole square, and naturally it is greater than 0 by the regularity conditions. Thus, from double star, the second order condition for maximizing L theta holds, because the second order derivative here is equal to minus k theta, which is negative. Hence, we prove the above result. Next we go to the another result related to likelihood equation. Suppose the second order derivative of Lx theta is less than equal to 0 for all theta belonging to the parameter space omega. Then theta hat satisfying del del theta Lx theta equal to 0 is the global maximum. As an outline of the proof of above result, we can say that small Lx theta equal to Lx theta hat plus theta minus theta hat into first order derivative of Lx theta at the point theta equal to theta hat plus theta minus theta hat whole square divided by 2 into second order derivative of Lx theta with respect to theta at the point theta equal to theta star for some theta star belonging to the open interval theta hat to theta. Naturally, it is nothing but the Taylor's theorem. Note that the right hand side is less than equal to Lx theta hat, because in right hand side the second factor of second term vanishes, because at the point theta hat the first order derivative of Lx theta equal to 0, and the second factor of the third term is less than equal to 0 by the given condition of the result. Hence, we can realize the above result. Next we go to the another result. Suppose the first order derivative of Lx theta with respect to theta equal to 0 if and only if theta equal to theta hat. Second order derivative of Lx theta is negative at the point theta equal to theta hat, and theta is an interior point of an interval which is a subset of the parameter space omega. Under these three conditions, theta hat is the global maxima. As an outline of the proof of above result, we can start as follows. If possible, suppose theta star hat is such that the log of the likelihood function at the point theta star hat is greater than the log of the likelihood function at the point theta hat. Then there exists a local minima in between the local maxima theta hat and theta star hat. Naturally, this implies for that minima point also the first order derivative of the log likelihood function small lx theta should be equal to 0, which is a contradiction to the given condition of the result. Hence, the uniqueness of the maximum likelihood estimator theta hat is established. Next we go to an application of the likelihood equation in some theoretical distribution like normal. Let x1, x2, xn be IID normal mu sigma square variables. Then the log of the likelihood function equal to some constant minus summation xi minus mu whole square divided by 2 sigma square minus n by 2 times log of sigma square. So naturally, the first order derivative of log likelihood function with respect to mu equal to 0 and the first order derivative of the log likelihood function with respect to sigma square equal to 0 gives the two likelihood equations. The solution of these two equations gives mu hat equal to x bar and sigma square hat equal to 1 by n summation xi minus x bar whole square, which is nothing but sample variance with divisor n. Also, here we can check that the second order derivative of the log likelihood function with respect to mu and sigma square at the point mu equal to x bar and sigma square equal to s square is equal to 0. The second order derivative of the log likelihood function with respect to mu square at the same point equal to minus n by s square, and the second order derivative of the log likelihood function with respect to sigma square at the same point equal to minus n by s to the power 4. So naturally here the Hessian matrix is H equal to a diagonal matrix whose two diagonal elements are minus n by s square and minus n by 2 s to the power 4. Obviously, it is not difficult to check that this matrix H is a negative definite matrix. This implies that the sample mean x bar and the sample variance s square is the global maxima point and is the maximum likelihood estimator of mu and sigma square. As the recap, we can say that today's discussion helped us understand how invariance property works for an MLE, what the likelihood equation is. We also learned sufficient condition for an MLE to exist, sufficient condition for unique MLE under regular estimation case, etc. Some examples showed how to solve the maximum likelihood estimator from likelihood equation.